Hi, I'm Dane Quinn from the University of Akron, and today's video lecture will talk about epicyclic gear trains. Epicyclic gear trains, also known as planetary gear trains, consist of three basic parts. There are central or sun gears that rotate on a single stationary axis. So for example, that's this large gear in the center in S. And then there are epicyclic or planet gears that rotate about that sun and are connected with an arm. So those are these smaller gears outside. If you notice, the example shown here on the right actually has two central gears. There's the large gear in the center, and then there's this ring gear on the outside. One distinguishing characteristic of these epicyclic gear trains is that the arm and all of the central gears rotate on a single axis. And that axis is stationary. So here, for example, NS, this large sun gear, and the ring gear, they all both rotate about this central point, as does the arm that sort of carries the planets along. Again, this kind of looks like a solar system, right? You have a sun here in the middle, you have planets that orbit the sun, and it has some specific advantages. There are, in particular, reduced load characteristics due to the multiple planets. So notice here I have three planets, and they would share the load, which means, of course, that the load on any individual planet is reduced. They typically have a compact size. They're really good for high torque applications, for example. They are found in your automobile system and lots of other applications. Now, one of the disadvantages, as you may kind of notice here, they're complicated. Right? They have lots of moving parts, right? Multiple points of contact. So they can be more complex to design and analyze. One simplifying feature of these epicyclic gear trains is that multiple planets are, at least kinematically, identical to systems with a single planet. And really that's because each planet does the same thing. If I go back and I look at the previous example, I had three planets. Well, they all rotate about the sun. They all spin with the same speed. They're just offset from one another. And that's going to be identical to the motion of this system with one planet. Again, in actual applications, we typically have multiple planets so that we can reduce the load on the individual planet gears. But for kinematic purposes, we'll just consider a planetary gear system with single planets attached to the arm. So again, these are more complex to design, but also to analyze. Speaking of analysis, let's go and set this problem up. So each gear will rotate with angular velocity. So for example, gear 2 here is going to rotate with angular velocity omega 2 in the plus k direction. We'll have gear 3, which is the planet, has omega 3 in the k direction. And then finally, gear 4 will rotate with omega 4 in the k direction. In addition to the angular velocity of each one of these gears, we also need to define the angular velocity of the arm, because it moves as well. And we'll call that omega A in the k direction. I'll point out, and we mentioned this when we were analyzing parallel gear systems, is that each angular speed is defined positive in the plus k direction. So kind of out of the plane. And that becomes really important when we deal with planetary gear systems. Now, the normal speed relations that we developed previously, they don't work. And it's due to the motion of the arm, right? So this arm can carry these gears around. However, if we think about the speed of each gear relative to the arm, then once again, we're back to the same relationships that we had for parallel trains. So let's define omega tilde, so I'll put a little tilde over this, as the relative speed of the gear to the arm, right? So that's basically going to be omega I minus omega A. Omega I is the speed of an individual gear. I could be 2 or 3 or 4 here. And then omega A is the speed of the arm. Again, because each gear is defined, its speed, as in the plus k direction, then this is the speed relative to the arm. So again, this is the angular speed relative to the arm. And then our normal speed relationships hold. For example, omega 3 relative to the arm, so that's omega 3 tilde divided by omega 2 tilde, is equal to minus n2 divided by n3. Right? So if I look again at the speed of gears 2 and 3 relative to the arm, we have our relationship as we developed previously. Likewise, if I look at omega 4 tilde divided by omega 3, so again, speed relative to the arm of this large external gear to gear 3, that's going to be plus n3 divided by n4. Again, as long as we define these speeds all positive in the plus k direction, then this works out nicely. And as a result, we can actually look at overall gear relationships. So for example, omega 4 tilde divided by omega 2 is 4 divided by 3 times the relative speed of gear 3 divided by the relative speed of gear 2, right? Because of course these omega 3s would cancel out. So this becomes plus n3 divided by n4 times minus n2 divided by n3. And that becomes minus n2 divided by n4. Now, back in terms of the actual speeds of each gear, well, omega 4 tilde was omega 4 minus omega arm, and omega 2 tilde was omega 2 minus omega arm, and that is minus n2 divided by n4. So what we see now is that we actually have 3 speeds over on the left-hand side. We have the input speed, omega 2, possibly. We have omega 4, but we also have the speed of the arm. So if I want to determine 1, then I need 2 input speeds. Here, for example, I could determine, or I could specify omega 2 and omega arm, and then I could find omega 4. Unlike parallel trains, where we would have 1 input and 1 output, now we have 2 inputs due to the additional complexity of these epicyclic gear trains. Okay, so let's look at a simple example. Let's fix, actually, the ring gear, right? So we'll fix omega 4 to be equal to 0. So essentially we could take this and we could ground omega 4. And recall that we define these speeds as omega 2, omega 3, and of course here omega 4, which is equal to 0 because it's grounded. Finally, the arm angular velocity is given as omega A. So for this system, let's determine the speed of the arm. So although omega 4 is equal to 0, right? It's identically equal to 0. The relative speed, which is omega 4 minus omega arm, is not equal to 0, right? So again, if you were standing on this arm and this system was moving around, right, you would actually observe a motion of gear 4 because you're stationary with respect to the arm. In terms of the ground, though, the arm is moving and gear 4 is fixed. So going back and thinking about what we had before, omega 4 minus omega arm divided by omega 2 minus omega arm is equal to minus n2 divided by n4. Well, omega 4 is equal to 0. So we can solve for omega arm. Right? In particular, let's go into a little algebra here. So on the right-hand side, we'll have n4 times omega arm. I brought the minus n4 to the left side. I'll take this and put it on the other side. It's equal to n2 times omega 2 minus omega arm. And as a result, we see that omega A, the angular speed of the arm, is n2 divided by n2 plus n4 times omega 2. So with this planetary gear system, the speed of the arm is less than the speed of the input gear. And again, here we fixed the ring gear, the outside external gear, we fixed that in the ground. Now, notice and recall that the distance between teeth on each gear has to be the same. Right? So we can actually write that in terms of the module. And here, m is defined as 2 times the radius divided by the number of teeth, and also a different quantity known as the diametral pitch, which is P. And P here is basically the reciprocal of the module. For historical reasons, the module is given in metric or SI units, right? So if you have a gear with a metric standard, they'll typically give you the module. The diametral pitch is usually given in English units, right? So if you have an English-British standard, then you might be given the diametral pitch. But they're defined in the following way. So we can relate the radius of the gears to the number of teeth. Right? So in particular, R is equal to m divided by 2 times n, or R is equal to n divided by 2p. Again, m and p are reciprocals, although often given in different units. So these have to be identical for conjugate gears. And that basically comes from the circular pitch, which we saw was the distance between teeth, right? Because that is essentially pi times m, right? Or pi divided by p. So if I look at this gear train, we actually have a relationship between the number of teeth in gear 2, gear 3, and gear 4. Just from geometry, if we think about the pitch radii, well, R2 plus 2 times R3 has to be equal to R4, right? So the radius of this large gear is the radius of the inner gear, the sun gear, plus the diameter, or twice the radius of the planet. And as a result, we see that R is m over 2, right? So I can basically factor out an m over 2 from each of these. And we get n2 plus 2 times n3 equals n4. So for these epicyclic gear trains, oftentimes the number of teeth in the conjugate gears must be in some sense related, right? So I can't just have any number of teeth on gear 4, right? It's got to be the number of teeth on gear 2, the sun, plus twice the planet. Now, we can also combine epicyclic and parallel gear trains. Here on the right, I've shown such an example, right? So I have a large gear 2 that's a central gear connected to a planet, gear 3, which is again connected to an arm. Then gears 2 and 4 are rigidly connected, and then 4 drives 5 in a parallel system. This is a side view here, right? So I have gear 2 and gear 3 and the arm. These form a planetary gear system. And then 4 and 5 are connected in a parallel train, right? So really, if I look at this, gears 2 and 3 are epicyclic. And then gears 2, 4, and 5 are parallel. I mean, here I could take out the arm in gear 3, right? And I would just have a parallel train between gear 2, gear 4, and gear 5. Or I could remove gears 4 and 5, and I would have an epicyclic train between gear 2 and gear 3. Notice, though, that 2 and 4 are rigidly connected. So let's go through and define the angular velocities, right? So we'll say that omega 2 is the angular velocity of gear 2. Of course, omega 3 is the angular velocity of gear 3. Omega 4 is the angular velocity of gear 4. Omega 5 is the angular velocity of gear 5. And then finally, omega A is the angular velocity of the arm. Once again, all of these angular velocities are defined positive in the k direction, which allows us to use our gear relationships relative to the arm for the planetary gear cycle. Those relative speeds for gear 2 and 3 are defined as omega minus omega arm. So, looking at the epicyclic gear train, omega 3 tilde divided by omega 2 tilde is minus n2 divided by n3. Right now, we're going to go through and relate the speeds of conjugate gears, right? So 2 and 3 are conjugate, right? They're acting together. And this is their relationship. Again, because they're epicyclic, this is in terms of the relative speed. 2 and 4 are related. So omega 4 divided by omega 2, well, that's equal to 1 because they're rigidly connected. Finally, 4 and 5 are conjugate in a parallel train. So omega 5 divided by omega 4 is minus n4 divided by n5. So here, I want to find the output speed given the speed of the arm if omega 3 is 0. Actually, this is kind of like a hand crank. So you could imagine that this was the handle. So you want to come up and grab this large handle and you want to crank it around. Well, you don't want it to spin in your hand because your hand's not going to spin with it, right? Your hand is basically going to translate around, I mean, in a circular motion, right? But your hand is not going to rotate as you turn. Instead, that circular motion of your hand will produce the angular velocity of the arm, right? So here, again, this is a hand crank, right? We're going to spin the arm with omega 3 equal to 0, right? So the gear 3 is going to just translate around. That's going to drive 2, which will drive 4, which will then drive 5. So if I look at this, we have two relationships here, right? So essentially, looking at this first one, omega 3 is equal to 0 minus omega arm, and then 2 minus omega arm is minus n2 divided by n3, and we can relate 5 and 2 because they're in a parallel train. So omega 5 divided by omega 2 is equal to minus n4 and n5. One thing to keep in mind is that the numbering here is just arbitrary, right? What's really important is what gears are in mesh. So for example, gear 3 and gear 4, they are not conjugate to one another, right? So there's no relationship between 3 and 4. Instead, there's a relationship between 3 and 2 relative to the arm, and there's a relationship between 2 and 4, namely they're rigidly connected. So let's go through and work through the algebra. Looking at this first relationship, right, we can solve. Omega 2 is actually n2 plus n3 divided by n2, right? I mean, this is just algebra, and that's times omega arm. So solve this for omega 2 in terms of the arm. And then we'll use that in this next relationship, right? So omega 5 here is minus n4 divided by n5 times omega 2, or putting this all together, we get minus n4 times 2 plus 3 divided by n2 times n5 times omega arm. So now we've taken a system that has both an epicyclic and a parallel gear train that are working together, and we've solved for the output speed, right? So this is omega 5 in terms of the input speed of the arm. So again, kind of a complicated gear train problem. It's got lots of different things. And in particular, it combines both epicyclic and parallel gear trains. So that's it. Thanks so much, and I will talk to you again. Bye.